Hello, calculus students. This lesson is on related rates. It's the idea that in certain relationships between two or more quantities, if one quantity is changing at a certain rate, how does that affect the changes in the other quantity? We'll begin exploring this idea with this first page. A square initially has a side length of 3 feet and expands in such a way that each side steadily gains 2 feet every 30 seconds. Fill in the table below. Well, first of all, let's take a look at a visual. I have a time counter here, and then we have a square that's initially 3 by 3. And then as we get to the first 30 seconds, the square has expanded by 2 feet on each side, so we are now at 5 by 5. And then continues to expand from there, each side gaining 2 feet every 30 seconds. All right, focusing on this table, when time is 0, we are told that each side initially had a length of 3 feet, which means that the area of the square at that time was 9 square feet. Now, 1 minute later, the sides will have gained 4 feet each. 2 feet every 30 seconds means 4 feet every minute. So the side lengths will be 7, and the area will now be 49, 7 squared. So gaining 4 feet every minute, we know that we'll have 11 feet at the 2-minute mark, hence an area of 121. We'll have 15 feet at the 3-minute mark, giving us an area of 225 square feet. And gaining 4 more feet in the next minute, we'll have 19 feet per side, and 19 times 19 is 361. Even though the side length is growing at a steady rate, meaning we gained 4 feet every minute, notice that the areas are not growing at a steady rate. We gained 40 square feet, then 72 square feet, then 104 square feet, then 136 square feet. So the area is not growing in a steady rate. Now express the side length as a function of time. Well, this is a linear relationship. The length starts at 3, and then every minute we gain 4 feet. So 4 times t, where t is the number of minutes. If you struggle coming up with this equation easily, then focus on 2 different data points. Keep track of t and L. When t is 0, L was 3. When t was 1, L is 7. Then the slope is the change in L coordinates, which is 4, over the change in t coordinates, which is 1. And then you can use L minus 3 is equal to this slope times t minus 0, because the relationship is linear, and this in the end gives us L must be therefore 4t plus 3. Now express the area as a function of side length. This is just asking us for the area of a square whose side length is L, so that's just L squared. Now express the area as a function of time. Well, all we have to do is do a substitution. We take L as a function of t and substitute it in for the L's in the area function. That gives us that the area therefore is equal to, parentheses, 3 plus 4t, quantity squared. This is a function that inputs a time and will directly output the correct area at that time. Now find the instantaneous rate of change in the area with respect to time at the moment when t equals 3 minutes. This phrasing, instantaneous rate of change in the area with respect to time, in math notation, is the derivative of the area with respect to time. So we're trying to find dA dt precisely when t equals 3 minutes. Now keep in mind the area is not growing at a steady rate. It's accelerating in the same sense that a car would be accelerating if you push on the gas pedal. You would expect the speedometer to be increasing as you push the gas pedal. And this is just like asking, well, what's the speed precisely 3 minutes into the process? I'm going to show you 2 different ways to do this. The first way will be beginning with the relationship a as a function of t, and then just differentiating this, treating t as the independent variable. So we'd have to use the generalized power rule. The 2 would drop, the base repeats, the new power is 1 less, so I won't write it. And then the chain rule times the derivative of the inside. Derivative of 3 is 0, and derivative of 4t with respect to t is 4. So dA dt, evaluated at t equals 3, just plug in a 3, this becomes 15, and then times 2 is 30, and then times 4 is 120. Now the units of this will be a unit of area divided by the unit of time. So area is measured in square feet, and time is measured in minutes. So our dA dt will have a unit of square feet per minute. Now, it makes intuitive sense that 120 is a reasonable answer because between minutes 2 and 3, our area gained 104 square feet, but between minutes 3 and 4, it gained 136 square feet. So we expect an instantaneous speed at time 3 to be somewhere between 104 and 136. Now let me show you a different way to do this, beginning with the formula that's area as a function of L. So the area is just L squared. What we're going to do is differentiate both sides with respect to t. Notice t is not a variable here. So we have to treat a and L as both implied functions of t. So we get dA dt is the derivative of a with respect to t, and the derivative of L squared will be 2L to the first times the derivative of L, L prime. And this L prime is a dL dt. Now keep in mind that L as a function of time is 3 plus 4t. So the derivative of L with respect to t is 4. Furthermore, at time equals 3 minutes, we know that the length of each side, plug 3 into this, we get 15, which we confirmed already in our table up here. So this information will be substituted in for our dl dt, and this information will be substituted in for L. And so we get, and I'll just use A prime, equals 2 times 15 times 4. Notice this is exactly the structure we had over here. We had 2 times, and then plug in t equals 3. We got 15 here, and then times 4. So these two different methods aren't different fundamentally. They're just using different notations. And of course, this gives us 120, and the units would be square feet per minute. Now, moving forward, we don't always have enough information to take this approach. Sometimes we don't know the exact function for L as a function of t. Sometimes all we know is this information, and this relationship. And if that's the case, then I would use this second method to solve this task. Okay, let's go to the next page. Suppose a circle is changing such that its radius in meters is given by the function below, where t is measured in seconds. So here's our r function. We have sine of pi t, which is a sine wave with a period change, but not an amplitude change. Well, the amplitude of the sine wave is 1, meaning that the sine of pi t will fluctuate between outputs of -1 and +1, which when you add 4 to these outputs, this means that the radius will fluctuate between 4 minus 1, which is 3, and 4 plus 1, which is 5, forever oscillating between these two lengths. Furthermore, at time 0, sine of pi times 0 is 0, and sine of 0 is 0, so the initial radius is going to be 4 meters. Using technology to look at this, we have at time 0, we have a radius of 4, and then as time advances, we get a circle that's changing in such a way that the radius fluctuates between 3 meters and 5 meters. Find the instantaneous rate of change in the area with respect to time at the moment when t equals 3.25. Using technology, here's time equals 3, and as we advance time, here's a circle at time equals 3.25, and then the circle at time 3.5. We can see that r was in a state of decreasing, which means that the area is shrinking at this time. So first of all, interpret this statement. Find the instantaneous rate of change in the area with respect to time. This means we are looking for dA dt, and then at the moment when t is 3.25. I'm going to convert this to a fraction. This is 3 1/4, so it's 3 plus a quarter, which is 12 quarters plus a quarter, which is 13 quarters, or 13 fourths. We know that r is equal to 4 plus sine pi t. Let's find dr dt, or I'll just write r prime for short. The 4 goes away. The derivative of sine pi t will be cosine pi t times pi, using the chain rule. So specifically at this time, the r value will be 4 plus sine of 13 pi fourths. So looking at a unit circle, counting the pi fourths, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 pi fourths, which is coterminal with 5 pi fourths, and the sign is negative rad 2 over 2. So we get the radius is 4 minus rad 2 over 2. And r prime at the same time will be pi times the cosine of 13 pi fourths, and the cosine is this coordinate. Again, negative rad 2 over 2. So we get negative pi rad 2 over 2. These are the values of r and r prime at this moment in time. Now let's express area as a function of r. Now the area of a circle is pi r squared. We can differentiate this expression now with respect to time. The derivative of a with respect to t will just be a prime, or dA dt. And on the right side, the pi will stay because it's constant times function. The derivative of r squared, the 2 will drop, multiply to the pi, so 2 pi. R, the new power will be 1, and then the chain rule times r prime. And r prime, of course, is dr dt. Now we just need to do substitutions. We want to find a prime at this moment in time of t equals 13 fourths. Well, we know what r is at this time, so we'll substitute 4 minus rad 2 over 2 in for r. And we know what r prime is at this time, so we'll substitute that in for r prime. So we get 2 pi times 4 minus rad 2 over 2 times negative pi rad 2 over 2. And now I'll reach for a calculator, and we get approximately negative 45.96. Now the unit of this rate of change is unit of area, which in this case would be square meters, per unit of time. In this case, time was measured in seconds. So notice a prime is negative. That means that a is in a state of decreasing, or dropping in value. Now the next question is find the instantaneous rate of change in the circumference with respect to time at the moment when t equals 3.25. Well, this is the same moment in time. So translating into math symbols, we are expected to find d, and then I'll write c for circumference, dt, once again when t is 3.25, or 13 fourths seconds. Now we've already done a lot of the legwork up above, so I can go straight to a circumference formula as a function of r. We know that the circumference is pi times diameter, which is 2 pi times r, because 2r is the same thing as diameter. Differentiate this with respect to time. We get c prime is equal to, the 2 pi will stay, and the derivative of r is just r prime. Notice there is no r in this statement, so the only thing I need to substitute for is the r prime, with the value in blue above. So that gives me c prime, which is dc dt, equals 2 pi times negative pi rad 2 over 2. This one I'll simplify is just negative pi squared rad 2, because this 2 and this 2 will cancel. Thus c prime, reaching for a calculator, is about negative 13.96. And the units of this, circumference is measured in meters. Circumference is a length, not an area. So this would be a unit of circumference per a unit of time. So meters per second. At this moment in time, the circumference is losing 13.96 meters per second because its rate of change is negative. So summarizing this in words, if you say rate of change in c, then you want to give the value with the negative. But if you phrase it this way, c is decreasing at the rate of, and here you would give a positive value because the word decreasing implies going down. So be careful, depending on how you phrase it, using language such as decreasing or losing or going down or dropping imply the negative, so you would just need to give a positive number here in this sentence. But if you say something neutral about whether we are increasing or decreasing, such as just rate of change, then make sure you have positive or negative value here as appropriate. Okay, let's go to the next page. A winch is pulling a rope to draw a boat toward a dock. The dock is 16 feet above water, and the deck of the boat is 4 feet above water. The rope is retracted at the rate of 2 feet per second. Determine how fast the boat is moving toward the dock when the boat is 20 feet from the dock. All right, using technology to animate this process, notice that we have the boat being pulled in toward the dock by a rope. What you want to be able to do mentally is to overlay some sort of mathematical geometry on the scenario, such as we have a right triangle that's changing shape. The rope is the hypotenuse, and then we have a height b and a distance a that the boat is from the dock. On this slide, I'm going to illustrate a 5-step process for tackling problems of this sort. Step 1, draw a static picture that represents the dynamic scenario. In the picture, label changing quantities as variables and constants as numbers. So to make my right triangle, now the quantities that are changing, A and C are both shrinking, but B remains constant. So the advice here is to label changing quantities as variables. So I'll have A here and C here for the hypotenuse, and this is a right triangle, but the height of the triangle is not changing, so we want a constant there, not a variable. We have to determine what that constant is. Now we're told that dock to water is 16 feet, but the deck of the boat, where the rope is attached to the water, is 4 feet. So the deck of the boat up to the dock would be a steady 12 feet. So in our dynamic image, you want to imagine this labeling, where the red length is 12 feet always, but A and C are changing. Now most of the dynamic imagery you must imagine when you're setting up problems like this. Step 2 is identify the givens and the derivative you are looking for and at which moment. Okay, parsing out the prompt, here's information that we've already interpreted, giving us that the height of the triangle is a steady 12 feet. The next bit of information that's given is that the rope is retracted at the rate of 2 feet per second. Well, the side of the triangle that represents the rope is C, the hypotenuse. So we are told that we are losing 2 feet per second. This is a rate of change of C. It's given that dc dt is 2 feet per second. And keep in mind that we are losing length. So the rate of change should be negative 2 feet per second. And then the next sentence frames our goal. The goal is to find how fast the boat is moving toward the dock when the boat is 20 feet from the dock. Well, the side of the triangle that represents how far the boat is from the dock horizontally is A. We want to find A's rate of change, so find dA dt at the moment when the boat is 20 feet from the dock. That means when A itself is 20 feet. Okay, now let's move to step 3. Create an equation that relates the relevant quantities. Well, the relevant quantities are C and A because I have information about C prime, I'm looking for A prime, and I have information about A. So I want to come up with a relationship that relates A and C. And because A and C are two sides of a right triangle, and the third side we also know, the most obvious relationship to use is the Pythagorean theorem as a starting point, which would state that A squared plus 12 squared, keep in mind that 12 is constant, so I don't need to put a variable there, is equal to C squared. And that's step 3. Step 4 is differentiate both sides of the equation with respect to the appropriate variable, in this case with respect to t. All right, so I'm going to take this equation and differentiate both sides with respect to t, and we know it's t because the speed up here was given per second, and seconds is a measurement of time, and a is a function of time, and c is a function of time, meaning that they're variables that change with time. So using the generalized power rule, the derivative of a squared is 2a to the 1 power, and then times the derivative of the base, so times a prime, and that a prime is a dA dt. Now the derivative of 12 squared will be 0, because that's a constant, and then the derivative of c squared will be 2c to the first, and then chain rule times the derivative of c, and c prime is dc dt. And this takes us to step 5. Substitute all givens at the moment in question and solve for the desired derivative. Well, the derivative we're looking for is a prime. We know that c prime is negative 2, and we want the moment when a is 20. 20 will go in for a. But notice this leaves c. I need a number to substitute in for c in order to isolate a prime and get a final result. Well, sometimes the way to do this is to draw a quick snapshot of the scenario at this moment in time. In other words, when a is 20, and the height is always 12. So at this moment in time, I'm actually able to find the value of c. This is basically a freeze frame of the scenario when a is 20. I can find the value of c. C squared is 20 squared plus 12 squared, which will be 544. So c is the square root of 544. This gives me the final piece of the puzzle. I can substitute this value in for c for this moment in time. Notice I can also divide both sides by 2, so these 2's will cancel. So substituting in the blue value, we have 20 times a prime is equal to the pink value, square root of 544, times the green value, negative 2. Therefore, a prime is negative 2 square roots of 544 divided by 20. I can simplify this a little bit. Negative square root of 544 over 10, which is about negative 2.33. A is a length, so dA dt will be a unit of length per a unit of time. So in this case, this would be feet per second. And notice the rate of change is negative, which means that A is decreasing, which makes sense given the scenario. So you could say that A is changing at the rate of, and then make sure you say the negative 2.33 feet per second. Or you can imply the negative in how you say this. You can say A is decreasing at the rate of 2.33 feet per second. And I did not need to say the negative when I used the word decreasing. Okay, we'll follow these 5 steps on the next slide. A right triangle with horizontal and vertical legs is changing shape. The vertical leg is growing 3 centimeters per minute, and the horizontal leg is shrinking 2 centimeters per minute. So using technology, I have an image of a triangle that is changing in this way. Now there's 2 questions on this page. Let's do the first one, which is to determine the area's rate of change at the moment the horizontal leg is 7 centimeters and the vertical leg is 5 centimeters. Well, step 1 is to draw a static picture, but of the dynamic scenario. So we have some sort of right triangle. Now the vertical and horizontal legs are changing, so I'll use variables for them, a and b, which means that also the hypotenuse will be changing. So the hypotenuse c will also be variable. So I see no constants in this triangle. Step 2 is to identify the givens and the goals. It is given that the vertical leg is growing 3 centimeters per minute. So we are given that dA dt growing, so positive, and 3 centimeters per minute. We also are given that the horizontal leg is shrinking 2 centimeters per minute. So the horizontal leg is b, so we have dB dt, and the fact that it's shrinking means I need to use a negative rate, so minus 2 centimeters per minute. Our goal, and I'll call this goal 1 because there will be 2 questions on this page, is to find the area's rate of change, so find d capital A dt, capital A for area. At the moment, the horizontal leg, which is b, is 7 centimeters, and the vertical leg, which is a, is 5 centimeters. So in our dynamic imagery, we want to find the rate of change in the area of this triangle at this moment, and then unfreeze, and the triangle continues to change shape. So next is to come up with an equation that relates the variables that are relevant. And the relevant variables are a and b, and then also area. Nowhere in the givens or the goals do we involve the hypotenuse. I need an equation, ideally, that involves area, a and b. Well, that equation, the area of this triangle, will be 1/2 the base times the height. If you copy this triangle and put the copy on top of it in this way, we'd have a rectangle. The area of the rectangle is a times b, so the area of the triangle is half of that. This is the equation that involves area, a, and b, and I want to differentiate it now with respect to time. Derivative of capital A will just be a prime, or dA dt. The 1/2 will stay, and then to differentiate b times a, I need to use the product rule. So we have the derivative of the first times the second, plus the first times the derivative of the second. And now I'm ready to do substitutions. We know dA dt, which is a prime, will be 3. We know dB dt, which is negative 2, will be b prime. B is 7, so this b will turn to 7. and A is 5. So that A there will turn to 5. And I have all the information needed so that A prime can be solved for. So we have 1/2. B prime is -2 times A plus B is 7 times A prime, which is 3. So you have -10 plus 21, which is 11 times 1/2. And 1/2 of 11 is 5.5. So in decimal form, we have the change in area is positive, notice. So the area is growing at this moment. And this would be square centimeters, the unit of area, per minute. Okay, in the second question on this page, determine the rate at which the shrinking angle is changing at the same moment. Well, looking at our dynamic imagery, this angle here is growing in size. This angle here is decreasing in size. So in my picture, the angle that I'm interested in, the one that's shrinking, is the angle up here, which I'll call theta. And our second goal is to find this rate of change in angle with respect to time at the same moment. So again, when B is 7 and A is 5. Now to accomplish this goal, I'm going to need to start with a different starting equation. Ideally, one that involves theta, A, and B. Well, relative to theta, B is the opposite side and A is the adjacent. So I see tangent or cotangent being great equations to begin with. I'll use tangent. We know that the tangent of theta will be the opposite of theta, which is B, divided by the adjacent of theta, which is A. This is the equation I want to start with, and then differentiate now with respect to t. Now the derivative of tangent theta will be secant squared of theta, and then chain rule times theta prime. And the derivative of b over a, I would need to use the quotient rule. So the derivative of b times a minus b times the derivative of a, all over a squared. Keep in mind that secant squared of theta is really the secant of theta and then being squared. Our goal here is to find theta prime. I have information to change any b I see to 7, any a I see, and there's 2 of them, to 5. B prime will be changed to -2, and a prime will be changed to 3. But I need to find a way to also replace this secant theta with a number so that I can ultimately find theta prime. So in this case, I will need to draw a freeze frame. We have theta, and the freeze frame is the moment when b is 7 and a is 5. I want to be able to use this as a reference triangle to figure out what secant of theta is. Well, the secant of theta is hypotenuse over adjacent, but the hypotenuse is not known yet. We can call it c. I know the 2 legs, so I can find c using Pythagorean theorem. C squared will be 5 squared plus 7 squared, so c squared will be 74. So at this moment in time, c is the square root of 74, which tells me that whatever theta is, the secant of theta will be hypotenuse over adjacent. So this value can go in for secant of theta. So we get theta prime, which is what I'm looking for, times secant of theta, which is radical 74 over a 5, that needs to be squared, is equal to b prime is -2, a is 5, b is 7, a prime is 3, over an a squared, a is 5. That'll be a 25 there. Well, squaring radical 74 over 5 will just be 74 25ths. This numerator will become -10 minus 21, which is -31, over 25. I can multiply both sides by 25 right now and cancel these. And now just divide by 74, and we get -31 over 74. Negative because theta is decreasing as expected. Now the units here will be units of the angle. And whenever you do calculus with trigonometry, we're always measuring angles in radians. So this would be a radian per, and then the same unit of time before, which is minutes. So theta is decreasing at the rate of 31/74 radians per minute, or you can say theta has a rate of change of -31/74 radians per minute at this moment in time. Okay, let's go to the last page. An empty tank of water in the shape of an inverted cone is being filled with water at a rate of 0.5 cubic feet per minute. The radius at the top of the tank is 3 feet, and the height of the tank is 4 feet. Find the rate at which the depth of the water in the tank is changing at the following moments. So this time we have one rate of change we're looking for, but at different times in the process. Using technology to create a visual, now the water is being poured in at a steady rate of 0.5 cubic feet per minute. And because there's less space at the bottom of the tank, you expect the water's height to increase rapidly initially, but that as time goes on, the height of the water changes more slowly because there's more space at the top. Now we want to be able to look at this from a side view and then remove some of the clutter. So the volume of the water is changing. The height of the water, h, is increasing, and the r, the radius at the top of the water, is increasing. In my picture, I'll draw a static representation of where my water is at. The radius is r, and the height is h. This was step 1. Step 2 is to identify the given and the goals. The first given I see is that water is increasing at the rate of 0.5 cubic feet per minute. Now, cubic feet is a unit of volume. So this is a rate of change in volume, a dV dt. It would be positive because the volume of water is increasing. So I'll use a fraction 1/2 cubic feet per minute. Now we do have two different goals. Goal 1 is to find the rate of change at which the depth of the water in the tank is changing. I'm calling that depth h. So find dH dt, and then at the moment when the water is 2 feet deep, when h itself is 2. I'll go ahead and state goal 2. Goal 2 is to find the same rate of change, but this time at the 20-minute mark. So when t is 20 minutes, and this h here is feet. Now the volume of water we can represent with a V. Since the water is in the shape of an inverted cone, you will need to recall that the volume of a cone is 1/3 pi r squared h. The r and h in this case we need to measure in feet, so r squared is feet squared times h gives us feet cubed, which is a correct unit for volume. Now the next thing I notice is that in all of our information here for the givens and the goals, I only see information about V and H. There's no information about R, so it would be ideal if I can come up with a VH relationship that is independent of R. So we've got to find a way to get rid of this R squared in a valid way. Well, this would be possible because R and H have a relationship due to the fact that the radius at the top of the cone is 3 and the height of the cone is 4. We can find this relationship by comparing similar triangles. Looking at the cone, we have dimensions 3 and 4. And then looking at the similar triangle of water, we have R and H. So if two triangles are similar, such as these are, then you can do all sorts of ratios and equate them. For example, you could say 3 divided by R is equal to 4 divided by H. I'll do the ratio of R to 3 is equal to the ratio of H to 4. And solving for R, we get R equals 3/4 of H. This is telling us that whatever H is, this R will always have to be 3/4 of it. This gives us the tools to express V now as a function of only H. So the volume of our water will be 1/3 pi R, which is 3/4 of H squared, times H. So I square 3/4, get 9/16, multiply that with the 1/3 in the front. That gives me 3/16 pi, and then we have H squared times H, which is just H cubed. This is the formula that I want to begin with, and the next step would be to differentiate both sides with respect to time. So the derivative of V will be V prime, or dV dt, equals the 3/16 pi is a constant times H cubed, so that constant will stay. So I need to use a generalized power rule. This 3 here will multiply to this constant. So 3 times 3/16 is 9/16 times pi. The power drops to 2, and the chain rule multiply by H prime. Now this question is asking us to find H prime. So I'll need to substitute 1/2 for V prime, and the moment in question is when H is 2, so that can go in for this H here. And there are no other variables here, so I can now solve for H prime. So 1/2 goes in for V prime. H is 2, so square that's 4, and times 9/16 will become 9/4 pi times H prime. Multiply both sides by 4 gives me 2 equals 9 pi H prime. So H prime, therefore, is going to be 2 over 9 pi, which is approximately 0.0707, rounded to 4 decimals. And this unit would be a unit of H. H is a length measured in feet per unit of time, and in this case, the time was measured in minutes. Okay, now goal 2. Also find dH dt, but when t equals 20 minutes. So I can take this same statement right here and copy it, and we still want to find H prime. I can still substitute 1/2 in for V prime, the green number, but I need to substitute something in for H, but I can't use the blue number because H isn't necessarily 2 at this moment in time when t is 20. So I need to figure out what H is at this time. Well, when t is 20, keep in mind that the tank started empty and we're gaining 0.5 cubic feet per minute. So 20 minutes later, our volume will be 10 cubic feet. Well, what's the H at this time? Well, I can use this relationship right here, substitute V in for 10, and solve for H. So we know that 10 will be equal to 3/16 of pi H cubed. We'll multiply by 16, divide by 3 pi, and then take the cube root. H will be the cube root of 160 over 3 pi, measured in feet. This value goes in for my H. So we get V prime is 1/2 equals 9/16 times pi. H is the cube root of 160 over 3 pi, and that H needs to be squared, and then times H prime, and I can solve for H prime. I'll multiply the 16 over to the 1/2, that gives me an 8, and then divide both sides by the rest of this, 9 pi, and then when you square the cube root, you could just write that as a 2/3 power, and this will be my H prime. Reaching for technology to round this, we get about 0.0428 rounded to 4 decimal places, and again, feet per minute. So in summary, sometimes there are cases where you are directly given all the information you need to make the substitutions, and solve for the derivative in question. And there are times where the information that was given, you had to create a freeze frame in time and figure out value that's actually necessary to substitute into your equation to solve for the desired derivative. So we had to convert that t equals 20 minutes ultimately into an h value that could be substituted in, and then I could solve for h prime in this case. Okay, and this concludes our lesson on related rates.